Hi, welcome to video number 47. This will be the first video in a series of videos in which we'll be using GERS-1 radar images to map out wetlands in the Middlebury, Vermont area. And we obtained these radar images from the Alaska Satellite Facility. And the first step in our workflow will be to take these images and convert them from their raw level 1 format into a GeoTIFF format using the freely available MapReady software from the Alaska Satellite Facility. So in this video, I'll give you a quick overview of radar imaging, and then I'll show you how to use the MapReady software. So one important thing to know about radar imaging is that it's deliberately collected in a side-looking geometry. So you'll typically have some aircraft flying in the azimuth direction, and it will be pulsing pulses of long wavelength microwave energy off to its side in what's called the range direction. So the range direction will be perpendicular to the azimuth direction. And each pulse images basically a strip of land. And one of the important things to know about radar imagery is that pixels are, one, not square. They have a different size in the azimuth direction than they do in the range direction. Two, the actual pixel dimensions change. The spatial resolution actually gets better as you go away from the satellite in the range direction, and the resolution in the azimuth direction actually gets worse as you go out away from the satellite. So one unique thing about radar imagery is that the pixels are not constant in size, which means we're going to need to resample them to get them into a usable raster grid format. So a couple other points about how radar data is collected. Radar images are collected using what's called a time for space transformation. Basically, the radar sends out a single initial pulse and then measures returning energy as a function of time. So in this example, all the radar antenna knows is that the first return came back at about 13 seconds, the second return came back at about 17 seconds. Because this return reflects a shorter slant range distance, and this is a longer slant range distance away from the aircraft, the basic image processing then maps this return to a land surface pixel that is closer to the aircraft. So in other words, this return came from the house, which is closer. This one came from the tree, which is further away. Unlike an optical sensor, radar is not exploiting a specific geometric relationship. It's actually using the return time of the signal to map out the distance away from the aircraft in the slant range direction. So this type of mapping works pretty well if the ground surface is flat. However, once you get into steep topography, we encounter some problems. Imagine there's a big mountain right here. You could imagine a case where the top of the mountain actually is closer to the aircraft than the bottom of the mountain in terms of direct range distance, even though it's actually further away in terms of its absolute ground distance. The problem here then is that a pixel on top of a mountain could actually be mapped as occurring closer in ground distance than it actually is. And so this leads to a problem called radar layover, in which mountain tops and other topographic high points are actually displaced in the image towards the detector. So consider this example. Here's a river flowing through some mountains with a lake. This is the optical image. Here's the radar image, collected with the satellite over to the right and shooting energy from right to left. You can see that the mountain tops are laid over. They're displaced closer to the satellite. And this creates a problem. If we want to actually display this topography in an orthographic projection that has an equal scale in all parts of the image, we'll need to actually restore some of this layover, actually move this peak back to its original location. Likewise, another thing you can see in this image is that the foreslopes of the mountains are much brighter than the back slopes. This has to do with the fact that you get a stronger radar return if your angle of incidence is perpendicular to the surface. So because the angle of incidence is perpendicular to this slope, they're showing up very bright because they're reflecting a lot of energy back directly to the antenna. The back slope of the mountain is experiencing a very low incidence angle, reflecting energy away from the antenna and showing up darker. So importantly, if we want to use the strength of the radar return to diagnose surface materials, we're going to need to correct for some of these topographic effects. We're going to need to correct for the effect of this incidence angle, and we're also going to need to do a geometric restoration, something like a rectification, where we actually move these pixels back to where they should be in an orthographic map projection. So the MapReady software is going to let us correct for a lot of these problems. And here's a list of 5 major things we'll be doing with the MapReady software as we process our images. First, we'll be ortho rectifying some of those terrain shifted pixels, moving the peaks of those mountains back to where those pixels should have been if they weren't laid over. We'll also be resampling the image into square pixels. Recall that because the pixel size varies across a radar image, we're going to need to resample those into equally sized square pixels so we can put them into a raster. We're also going to correct for the measured amplitude. So we're going to use a digital elevation model to figure out what the slope and aspect of each surface is. And then we're going to make the adjustment for those different incidence angles to try to restore the measured signal back to what it would have been if all of the surfaces had the same incidence angle. Finally, we'll do some practical things. We'll change the file format into a gridded GeoTIFF raster that we can easily manipulate in ArcMap and Envy, and we'll be projecting the image into a universal transverse Mercator projection that has a constant scale throughout the image. So before we get started, I want to show you where you can get the MapReady software. That is simply on the Alaska Satellite Facility website. Just Google ASF and MapReady, and you can download the software as well as all the literature that describes how the software works. Now, importantly, if you're working in a Sunderland computer, the only way to start up this software is going to be go into the Windows Explorer, find the computer icon, open up the C drive, go to Program Files. Within Program Files, you should find ASF Tools. Within that, you'll find the MapReady folder, and then scroll down until you get to mapready.execute and double-click that to launch the program. So here you can see the interface, and it's divided into 3 parts. The top part, you've got your processing parameters that you can specify. The middle part, you're going to choose your input files, and then the bottom is going to show you once they've been processed. So let's first pick a few of our input files. If you haven't already, make sure you've copied the Lab 9 folder, or Lab 11 folder, into your personal workspace. Go ahead and browse into that workspace, and you'll find the data folder, find the raw radar folder, and within that you're going to find the 2 different images that we're processing. Here they are. So I'll open those. Now to specify the output file name, click a destination folder, and why don't we put these into a new folder called Processed Radar. So I'll hit OK. So those are going into the Processed Radar folder. Now I'm also going to adjust the file name. I'm going to replace this last extension with the extension AMP. That's going to be for amplitude, because we're going to process these into amplitude. Okay, so those are ready to go out. Now let's have a look at specifying some of the processing steps we want to use. So in this MapReady, you can choose some external programs If you click this box, notice this tab lights up. This will let you do a bunch of different resampling, smoothing operations, but we're actually not going to use that. We're not going to use the polarimetry. We are going to use the terrain correction, okay? So under terrain correction, there's a couple different things we can ask it to do. First, it's going to apply a terrain correction. We're going to have it perform a co-registration, so we can try to tightly register our image to the topography. We're going to have it apply a radiometric terrain correction, so that will correct for the effect of the incidence angle on the measured amplitude. We're going to have it interpolate layover and shadows. So any place we have bad layover, it's going to interpolate those data. We're not going to save either of these things. Now we need to tell it what digital elevation file we'd like it to use to do these corrections. And we're going to find that under the elevation folder. And we're going to choose the Champlain Valley SRTM 90-meter data. And make sure to leave this Apply Geoid Correction box checked. So a couple other things. Under Export, we're going to export to a GeoTIFF format. We're going to export all bands as separate images. We only have one band. And leave everything else at the default. Under Calibration, we're going to leave this as Amplitude. This has a bunch of different choices. You can compute the backscatter cross-section and a bunch of other interesting features. Also, I'm going to check this box, Keep No Intermediate Files, so that we throw away all the intermediate files. And a final thing we need to do is actually check this box, Geocode to a map projection, and then get to the Geocode tab and make sure we've got the projection set to UTM and zone 18N, which is the zone Vermont is in. And we can leave the pixel size at default. I like to use the bilinear resampling as opposed to the nearest neighbor. Okay, so in summary, this is what your general settings should look like. This is what your calibration settings should look like. Your terrain correction, your geocoding screen, and your export screen. So now we're ready to go. I'll hold down Shift and I'll highlight both of these files, and then I'll click Process All to start processing them. So once you've started processing, you should have this command line interface that pops up, and you can follow along with the processing steps. Note that processing is going to take at least an hour for a couple images. So please go ahead and get your images started processing, and then move to the next video where you'll be able to keep going without having the images fully processed. So in summary, we've processed level 1 radar imagery with the MapReady software. This is going to allow us to ortho rectify terrain shifted pixels. It's going to resample the image into square pixels that can be housed in a nice raster. It's going to correct the measured amplitude for the incidence angle, also known as the topography. It's going to output a GeoTIFF file we can use, and that GeoTIFF is going to be projected into a UTM projection. So please join us for our next video, video 48, where we'll take these processed GeoTIFFs, bring them into NV, and work on making sure they're projected carefully. Thanks for listening.